Okay, let's look at deletions now. So recall that in general, when we delete a node, I think at the beginning we had seen that there are three cases we are in. If we delete a leaf, uh, in the old way of doing things, there was nothing more to do. If we had to delete one child also, that was relatively straightforward. If we had to delete two children, then we had to uh, you know, uh, exchange the values with the predecessor or successor of whatever it is we are trying to delete, and then physically delete the predecessor or successor, which will have only one child, and hence it's easier to pluck out physically that node. So in either case, with the node that we are physically plucking out will have at most one child. Right, so let me just make a note of that. The node that is physically deleted is either a leaf or a node with one child. The node that is physically deleted could have, when we say one child, this could be an entire subtree. Right? Possibly there could be an entire subtree there. So it's not like it has a single leaf node that is a child, because the successor of whatever it is we are trying to delete could lie anywhere. It won't have a left child, but it could have a right child, which could itself be a, the root of a large subtree. So when we look at, let's say x is the node that we were trying to delete. So x could have been the left child or the right child of its parent. So it doesn't matter how we pluck out x, what it will have some child. I'm just showing it vertically because it doesn't matter whether it's a left child or a right child. What we do is we are bypassing x, the node that we are physically plucking out, and making the parent pointer to x point directly to its child. By doing so, what happens to the height of the parent? So, or I should say height of the subtree containing x. Right? The parent might have another subtree whose height might not change, will not change, but the height of the subtree containing x reduces by 1. Whichever direction that subtree was in. So if x was was the left child of its parent, then the branching factor of the parent is going to reduce by 1, because the height of the left subtree has reduced by 1, and the branching factor is the height of the left subtree minus the height of the right subtree. When we deleted x and x was uh, the right child of its parent, the branching factor of the parent is going to increase by 1. Okay. Now, so there are actually three possible cases that we could have, and let me write them down. So when the branching factor of the parent reduces by 1, maybe it was 0 and it became -1, right? Or maybe it was 0 and it became +1. That's one pair of alternatives. Maybe the branching factor was already a 1 here. So let me write that in different color. Maybe it changed from +1 to 0, or it increased from -1 to 0. And the third case is maybe it was -2. Sorry, not -2, -1. It was -1 and it reduces to become -2. And here maybe it was +1 and it increases to become +2. Right, these are the three possible values that the branching factor could have had before the deletion, and after the deletion, these are the three resulting values that could have that it could take. Likewise, in this case. So what we want to do is to analyze each of these three cases and see what to do to fix things. So let's first look at the green case. The parent had a branching factor of 0 and it became -1. Or +1. Not height, sorry, a branching factor of 0. So parent had a branching factor of 0. So that means it had another child and it had X. So actually, before we come to that, if you look at the subtree here, this could be a relatively big subtree, right? Under whatever the subtree was under X. Will the branching factors there change? Well, no, because that subtree, the integrity of that subtree is not changed. Likewise, if there was another subtree here or subtree here, even the branching factors there won't change. So we have to focus on P, and P is where the change happens. So what would happen if the branching factor was 0? That means things were balanced on both sides of P, and by the removal of X, now suddenly things become slightly imbalanced. Are there going to be any repercussions of that further up? So to see whether or not there will be repercussions, what is important is the height of the subtree that's rooted at P. If P had a balance factor of 0, that means the left and right subtrees were equally balanced, and the removal of X made one side slightly imbalanced, but nothing to worry as far as violating the AVL property is concerned. The right subtree or the other subtree continues to have the same height. So the height of P does not change, which means when we look at any ancestor, grandparent or above, they are not going to find that suddenly the height of one of their subtrees has changed, and so their balance factor is not in any danger of changing because the height of the subtree rooted at P did not change. Okay, so that means, so the green case is the following: the height of subtree rooted at P didn't change. So no further repercussions. No repercussions at all actually. We just update the balance factor, and apart from that there's nothing to do beyond that. Let's look at the orange case. Um, so the parent was slightly imbalanced, and now it's perfect. So the removal of X causes it to be perfectly balanced. So think of what this implies about the height of the subtree rooted at X. Obviously, there's no problem as far as the balance factor for P is concerned. It's fine. But are there going to be any repercussions further up um, when the balance factor changes from +1 or -1 to 0? So the height of the subtree must have decreased by 1. Decreased by 1. One side was the side that was slightly taller has been trimmed, and so the overall height of the subtree rooted P decreases by 1, and this can have an impact on some ancestor because it could change the balance factor of some of the ancestor. So we keep going up. Looking for repercussions on the ancestors. The third case is where things are going wrong at the parent itself. The balance factor of the parent is violated, and so we need to fix things. And again, even though we are looking at the parent, note that the parent could have two subtrees now under it. Right? It's not like the simple case we were looking at the beginning of insertion where we had a node X, we had its parent, we had its grandparent, and we're just looking at 3 nodes. This time, the imbalance at P in the red case is a case where we can have arbitrarily large subtrees on either side. Okay, but we know P is the first parent, first ancestor where there is an imbalance. Now, because it could have two arbitrary subtrees on either side, even if the imbalance had not first occurred at the parent, but it had occurred at some further ancestor up, we can diagrammatically show them in a general way. Right? Let A be the ancestor where there is a problem that happens at the first, the first time. So A has a left subtree, it has a right subtree, and there is a problem at A. What is the problem? The problem is that one of the subtrees became slightly shorter, and that led to a violation of the balance factor at A. It doesn't matter whether A is the immediate parent of the node that was physically deleted or some higher up ancestor. Everything gets subsumed in this case only. So what I will assume is that either the right subtree became shorter or the left subtree became shorter. We don't know which one, but in general it could be either. So two cases, either A of L has a height of, so let's say the balance factor here is +2. Right? If it's +2, it must be because one of the subtrees has height h, the other has height h +2. The other case is where the balance factor became -2, in which case the height of the left subtree is h, the height of the right subtree is h +2. And x was deleted from the shorter side in either case. And x is no longer there, so I don't have to show x the way I had to show it when I'm inserting. X is not there, we just have two unbalanced subtrees. I mean, we have a node that has lost its balance, and we need to fix things. So I'm going to focus on this. Everything here will be symmetric. So we'll elaborate on this. Now, how do we fix this? Well, we have to look in slightly more detail at what is going on here. What is the structure here like? So there are three cases. So A sub L, the left subtree, has a height of h +2. Now, how could it have a height of h +2? If I zoom in one more level, actually, let me draw it here. I'm just going to show it as being composed of a root node B and a left subtree B sub L and a right subtree B sub R. So there are three possibilities. One of them is that three possibilities as far as the heights are concerned. So this total height is h +2. So the three possibilities are height of B sub L is h +1 and B sub R is h +1. Both have the same height of h +1. Second possibility is that the height of B sub L is h +1 and the height of B sub R is h. And the third possibility is that the height of B sub L is h, the height of B sub R is h +1. And as you'll see, there'll be three different things that we'll need to do for each of these three cases. So you have to unpack these three cases. So let's look at the first case. Let's say the height in both cases was B +1. So case 1, B sub L and B sub R are both h +1, h +1, and this is B sub R, which is of height h. So what can we do to fix this imbalance? The balance factor at A is h +2 minus h, which is +2. Let's see. Any suggestions? Surjit? You had a question or wanted to answer this?
Sorry, I kind of didn't lower my hand.
Okay. So Since it's not clear, there's no X here. I don't know how to even classify this. Um but it looks like the left side is heavier, and it's as if, it seems analogous to the case where we insert a number on the left side and the left side becomes heavier. So uh, let's treat it as being one of the two L cases, right? LL or LR. I don't know which one we are in, but let's just try LL since it's a single rotation and it's easier. Let's see what happens. So B.
I have a question.
Yeah.
So I'm trying to figure out why the balance factor is 2 at node A in the first place. Let's say at the BL, okay, what could be the balance factor at B? It has to be 0, am I right there?
Not necessarily. It could be +1 or -1 or 0. That's why we actually have these three cases. Because the balance factor at B could be any of those three.
Yes, we are analyzing the first case where BL is H+1, BR is H+1. So
Yeah.
the balance factor at B has to be 0 because the left
Yeah.
subtree height is same as the right subtree.
Right.
So if the balance factor at B is 0, then A has to be either -1. Can you go back to the right slide?
No.
Yeah.
So A could still be +2 because the change happened on the right side. Right, X was deleted from the right side, so the height here is H+2, and the height in the right subtree was previously H+1, but the removal of X somewhere inside that subtree caused the height of that subtree to become
So
H.
when you're saying the X was part of the AR subtree?
Right.
Okay.
So if you look at these two cases, we are you
Can you point which two cases you are talking about here? Can you point?
X.
Okay.
So the two cases. So case one here was X removed from A sub R, leading to this problem. The other case was X was removed from A sub L, leading to the other symmetric problem. Right now, A could have been the immediate parent of X, which which got a balance factor of +2 or -2, or maybe the parent itself didn't have an issue because the balance factor became 0 there, but some ancestor, right? There were repercussions further up. You kept updating the balance factors up and up and up until you reached a node A, some ancestor A, whose balance factor you had to update to either +2 or -2. The first such ancestor. And you have to do that update because one of the two subtrees from which you came got shorter. Does that make sense now?
Yeah. So basically so you're removing X from the AR of the left side, okay.
Yeah.
Yeah.
And we are looking at the left side in more detail. We are saying we don't need to look at the right side separately because it's just symmetric. Now, the removal of X caused this imbalance. So we are now actually looking not at the side from which X was deleted. So when we were inserting X, we were focused on the structure of the subtree into which X was inserted. Here, X was removed, it's gone. So we are now looking at the structure of the other subtree. And we are saying it could have one of these three substructures. because that's where things have to uh, come from. Right? Things have to move from the left side to the right side here so that balance is reachieved. So since we don't, it's not clear what to do, let's just try the simplest rotation, which is LL, and see if that restores the balance. So that's going to bring B. So B rises up, pushes A down. That's the direction of rotation. So the right subtree of A continues to be what it is. The left subtree of B also continues to be what it is. But the right subtree of B is going to become the left subtree of A because there's no space for a third child for B. So it just moves down to wherever. But those nodes are the ones that contain the successors of B. So we move them down in the left subtree of A. So in terms of Inorder Traversal, it's BL followed by B, followed by BR, followed by A, followed by AR in both diagrams. Now what happens to the heights? So let's mark the heights. A sub R has a height H, B sub R has a height H plus 1, B sub L has a height of H plus 1. And so now if you look at the balance factor at B, the left subtree has a height of H plus 1. The right subtree, by the way, the balance factor at A is plus 1. The right subtree has a height of H plus 1 plus 1, or H plus 2. So the balance factor of B is now minus 1, which is fine. It's a valid uh, value. We have to look at the height though. Somebody had asked, can we just look at the balance factors? I don't know. I mean, looking just at this balance factor itself is not giving me any information, particularly given that this is a new a new node that has occupied the space of this. Uh, Previously there was A, now it's B. So what does it even mean to just look at the balance factor value? Let's look at the height. The height of this tree on the left before rotation was H plus 3. Height before rotation was H plus 3. The height after rotation so if you look at this path, this yellow is this orange path. The height there is H plus 1 plus 1 plus 1. So all the nodes achieved balance. The height of the whole subtree did not change. So why should the managers above me have to bother? Right? Things they can remain oblivious to what happened. We can stop. So looks like LL did succeed. I hope this case is clear. This is the, this particular case. Let me actually take the third case next. Okay, so so I'll draw the same diagram, A, B, zooming in on the left side. A sub r has a height of h, and between B sub L and B sub r, this time it is B sub r that is slightly taller than B sub h, B sub L. They are not equal this time. Case 1 was when they were equal. Now they are not equal. So what do we do in this case? Because here also the branching factor at A is h plus 2 minus h, which is plus 2, which is a problem. Now if we had to pick a rotation to do, maybe it's not clear right now, but if you focus on which seems to be the heaviest section of the subtree on the left, it seems to be this path. Follow one step left and then go one step right, because this has the deepest height. So it looks like that needs fixing, and we can confirm that. Let's just try what will happen if we do an LL rotation. If we do an LL rotation, we'll do B here, we'll put A there, we'll put AR there. B sub L continues to be on the left, and B sub R comes here as before. But this time the height labels are H here, B sub R is H plus 1, A sub R is H. So when we compute balance factor at B, it's H on the left side, that's the height of the left subtree. On the right side, the height is H plus 2, because B sub R with A as its ancestor together make up a height of H plus 2. So this did not fix things the way we wanted. So it looks like this path is the path to focus on, since it has the heaviest or the longest length, and it's basically LR, analogous to LR. So let's try LR and see what would happen. Let me just mark this as did not work. So if we do LR though, you might remember that we needed a C as well. We can't just, we have to zoom further into B sub R. So this subtree is going to be of this form, C sub L and C sub R. And after LR is done, that's a double rotation. Between A, B and C, B comes first in Inorder Traversal, then C, and then A. So C is in the middle. So C is going to rise up with B to its left and A to its right after LR. The left subtree of B continues to be where it was before. The right subtree of A also continues to be where it was before. But the two subtrees under C are broken up. The left subtree of C is on the left side of C, so it's going to go here. The right subtree of C is on the right side of C, so it's going to go there. Now, what can we say about the heights? So this height we know was H plus 1. C makes up one of those numbers. So between C sub L and C sub R, at least one has a height h. Right, both of them could be h, but it's possible one of them could be h, the other could be h minus 1. It can't be h minus 2, otherwise there would be a violation at C. We know there is no violation at C because it was there since before we deleted x. So things were fine as far as balance factors at C went. So but at least one of them has height h. Right, so let me say less than or equal to h here, but one of them being h. B sub L has a height of h. A sub R also has a height of h. So the balance factor at A, so depends on whether C sub R had a height of h or not. So it's going to be either 0 or minus 1. Likewise, the balance factor at B will be either 1 or 0. We don't know which one. But if you look at the balance factor at C, the height of the left subtree at C is h plus 1, because B followed by BL gives you a height of h plus 1. And even if CL had a height of h, even if this had a height of h, it would still be h plus 1. So h plus 1 on the left side, h plus 1 on the right side. Doesn't matter which path you pick. If this had a height of h, then it would be h plus 1 here as well. Otherwise, this is already h plus 1. So the balance factor becomes 0. But C is a new node. So again, I can't tell just from the balance factor what the what the repercussions are. Let's look at the heights. So the height before rotation, before the LR rotation, was h plus 1. So if you follow this path, it was h plus 1 plus 1 plus 1. It was h plus 3. And now the height after rotation is so this is h plus 1. So we saw that both subtrees of C have a height of h plus 1. That means the subtree rooted at C has a height of h plus 2. This means that the height has reduced. We have achieved balance within the subtree, but the height has reduced. So after doing the rotation also, local balance has been achieved, but it's possible that there could be repercussions further up. This never happened in insertion. Whenever we did a rotation, after rotation there was no impact on the, there were no repercussions on the managers above. But here, even after fixing things, the manager above needs to be informed to look at repercussions there. And maybe there also we end up in a similar case like this, where maybe at the manager level things are out of hand, the balance factor has become -2 or +2 maybe, and again we are in this kind of case. So maybe the manager could fix things with a single or with a double rotation like this, but because the height of the subtree would be slightly smaller, there could be repercussions further up. And so what's happening here is we could potentially get a sequence of rotations in deletion which did not happen in insertion, and that's what makes deletion more complicated. So anyway, this was case 2. Any questions about case 2?
Can you
Hasan?
go back to the previous slide? One more slide, one more back. Yeah. So here, when you say case 2, you're talking about the okay. Case 1, yeah.
Let me actually.
Yeah, I got a little confused when you
Yeah,
mentioned
so people who
last
see
one
the
and
slides might get confused. So let me actually renumber them, and let me just call it as case 3. Okay, so now it should be fine. So now let's. Oh, yeah, Vasan, you had a question?
Yeah, Omkar, can you please explain the next slide? The blue C when you added, right? Can you explain the rotation, please? I kind of lost. I couldn't get it. Sorry.
So we are in the LR case, and I'm just recollecting that in the LR case, we need to zoom into this subtree,
Correct.
right? Because if we don't, that's a single rotation.
Correct.
So, so I just zoomed in and I said, well, this BR can be expanded into C with two subtrees CL and CR under it.
Correct. Correct. Yeah.
If BR has an overall height of H plus 1, that means at least one of CL and CR should have an overall height of H. So then when we do the, we just did the LR rotation like we were doing before. That is, focus on A, B, and C. What's the Inorder Traversal? B followed by C followed by A. That's the order in which you will hit the vertical protrusions when you do the boundary walk. So C is in the middle, B is first, A is on the right. That's what I put here.
Okay. Got it. Okay.
And then whatever was to the left of B stays to the left of B, whatever was to the right of A stays to the right of A. Whatever was under C now gets split, partitioned into, because everything in the left subtree of C has to be in the left subtree here.
Okay, so you're replacing BR logically with C, CL, and CR, right? That's
Right. Yeah.
Okay. I thought, where did BR go? Sorry. Thank you.
Okay, let me also.
yeah, Omkar, I'm just trying to figure out what could be the time complexity in case 3 applying the LR principle.
Each rotation, whether it's LL or LR or RR or RL, can be done in constant time. Obviously, the constant factors will be different because there'll be more. You can implement a double rotation. LR is a double rotation as a sequence of two single rotations, as mentioned before. So, but two constant time single rotations are still constant time double rotation. Or if you want to directly implement the double rotation by changing the pointers, that also, you can do it directly also. You just have to write separate code for it. If you look at a double rotation as a sequence of two single rotations, then once you have the code written for a single rotation, you can reuse it, two times in sequence. That's what makes it a little easier. That's why we have this terminology of single or double. But otherwise, you can directly manipulate the pointers also here to directly create this structure. You just have to write code then for all the 4 cases separately. Does that make sense?
Yeah, it makes sense, but I'm still, how can it be done in constant? Because in LR case, when we came down to the BR, we zoomed in and then we made C as the root and then CL as the right subtree for B and CR as the left subtree for A. How will it be done in constant time?
Well, how many links do you see here? Notice that we don't care anything about what's inside A sub R, B sub R, and B sub L. We haven't changed anything inside them. What we have changed are these 4 links. right? The links between A and B, B and BL. Well, actually, even between B and BL, things have not changed. Between B and C, things have. So this was zoomed into, but that just led us to 2 extra links because we just
Yeah,
zoomed in
there we
one
have to
level.
figure out whether CL, which one is H plus 1.
No, we don't have to. We just, for the purpose of analysis, um, I claim
But
that
then
one of the, at least
how
one
do you
of them.
link?
So whatever was CL, so you're going to say B dot right is equal to C dot left. Once you have a pointer to B and C, you will update B dot right to be equal to C dot left. That will
No, see,
create
the
this
thing
link.
is, see, in the blue color you wrote, at least one of them has a height H.
Hmm.
Okay.
Yeah.
Now, now the next step is you are saying, B dot right equal to CL.
Yeah. Hmm.
Yeah. So, in order to have a balance factor of 1 or 0, don't you have to figure out what is the height of CL versus CR before you link to?
No, because this is a general case, and we know that. So that's why we first do the analysis. We first, when designing the algorithm, we make sure that it's going to work correctly. It doesn't matter what the specific heights of CL and CR are. If we are in this particular case, H is a general value, right? Your algorithm has to run for any value of H that is meaningful. So if we are in case 3 here, H could be 0. It's possible that H could be 0, or it's possible that H could be 1, it could be 2, it could be 10, it could be 100. But the what we are saying is it doesn't matter what it is, because I can argue for a general H that things will work out. So my algorithm is going to work for any general H. I don't have to
So then I can
care about
also
what it is.
point B right to CR and A left to CL. That is possible.
Yeah, B dot right is this pointer, right? B dot right is
Yeah.
the right child of B. We are saying let's update that to the left child of C. Now, if the left child of C is null, it's going to get updated to null. That's fine.
No, what I'm saying is, can I make B dot right to CR?
No, because
Okay, because
after
C has to be
rotation,
on the, I got it. Okay.
after rotation, CR has to be on the right subtree of C.
Yeah, okay, I got it. Thank you.
Abhishek?
Yeah, Omkar. So the balance factor, so ultimately what we are trying to achieve here is height balancing, right?
Yes.
And the balance factor that we are calculating, that is just used for a local decision of how do we rotate so that we locally achieve the height balance.
Yeah.
But even after achieving the balance factor to be 0 after all the rotation, we still have to go back all the way to the root if required to check whether the balance factor got affected or not.
So, yeah, it depends on the case though. Suppose we were in case 1 where the height
Right.
before rotation and
Right.
after rotation did not change.
Right.
Then we don't have to go further up to the root.
Mm-hmm. Okay.
But if we were in case 2, we cannot be satisfied with this. We still have to, page the manager that
Right.
the things are leaking into your zone now. You need to make sure that things are correct. Even after cleaning up here, something still spilled up, and so you're telling your manager now. When your manager looks at the imbalance there at his or her place, maybe they find themselves in case 1, in which case after they have cleaned up, they stop. So it really depends on which of these 3 cases you fall into in each step. If you fall into case 1, you're going to end there. If you fall into case 2, you would case 3 here, you have to keep going up. And we'll see what happens in case 2.
Sure. Thank you.
So let's see case 2. What was case 2? Case 2 was when the height of the left subtree here is h plus 1. So case 2 is where this subtree has a height h plus 1, this subtree has a height h, and AR has height h as well. Right, going back to this diagram, this is where we are. B sub L has a height h plus 1, B sub R has a height h. Okay. Now, if we use our same gut feeling, saying that the heaviest or the tallest path seems to be like this, right? L followed by L. Let's try an LL rotation and see if things work out. So LL rotation will be done like that. So B rises up. A becomes its right child. A's right child continues to be AR. B's left child continues to be B sub L. But B's right child now has to go in the right subtree of B. It's going to go immediately here, so that in Inorder Traversal it will be caught first. By the way, did I write the Inorder Traversal here? No. If you look at the ordering here, it was LR, so we did this in the rotation here is identical to the rotation we did in insertion, right? B sub L followed by B followed by C sub L followed by C followed by C sub R followed by A followed by A sub R, before and after rotation. So here also, let's see, the order in which we'll do Inorder Traversal is first B sub L, then we'll hit B, then we'll hit B sub R, then we'll hit A, then we'll hit A sub R in both diagrams. Now let's put in the heights here. B sub R is h, B sub L is h plus 1, A sub R is h. So first let's look at the balance factors. Did we actually fix things? So the balance factor here is 0. The balance factor at B is h plus 1 on the left side and h plus 1 on the right side. So the balance factor became 0. But it's a new node. Let's look at the heights. So the height before rotation was actually h plus 3, irrespective of which case we are in, right? Because that's just an artifact of the fact that we are in this broad case where the height of this whole thing is h plus 3. So that I can fill in height before rotation is h plus 3. What about the height after rotation? So after rotation, this height is h plus 1. On the left subtree BL side also we have a height of h plus 1. So when we go up to B, including B, we would have a height of h plus 2. So the height has reduced. This means we have to continue going up and look at any repercussions further up. So even though it was a simple LL rotation which fixed things, we still have to go up. Here it was a more complicated LR rotation which fixed things locally, but we still had to continue going up. Case 1, LL rotation.
So we have to go up all the way until the root. The height has to be h plus 1 then. That's the max. Is that true?
Yeah, so obviously the maximum you can go is up to the root. And if the height of the root itself decreases, then there won't be any further repercussions after that, because at least the local
No,
balance.
what I'm saying is right
Hmm.
now at this stage the height is h plus 2. We have to go all the way up until the height reaches to h plus 1. That's the question.
No, we are looking at the height of the subtree rooted at A. We don't know how much of the tree is above us. Just that local subtree, we are calling h as the height of um, this subtree on the right side of A, and h plus 2 is the height of this subtree on the left side. We don't know how big the rest of the tree is. It could be 100h or whatever. Right, whichever node we noticed a problem in, we first fix the subtree there before expanding further up. And obviously, as we go further up, we are looking at bigger and bigger subtrees with potentially bigger and bigger heights. They will have bigger and bigger heights. So what the value of h when we draw the diagram for an ancestor is going to be more than the value of h that we have here. Does that make sense?
Yeah, a little bit. So so can you go back to the extreme right slide, whatever the orange
Or
one
extreme.
more? Yeah, yeah, there. No. Yeah, height has reduced. Continue going up.
Height,
So when you say
when I say height, I mean height of the subtree rooted at A has reduced after rotation, not height of the whole tree.
yeah, oh, okay, because when you mentioned the height of the rotation h plus 3 and then h plus 2, that's what I was thinking. Height has reduced from h plus 3 to h plus 2. So that means we still have to go up.
No. It's just that things were skewed, and after rebalancing, the subtree became shallower as a whole because things are more balanced now.
Okay. Yeah. Okay.
But the subtree became shallower, so that might cause an imbalance further up, because maybe things were already slightly imbalanced further up, and this subtree becoming shallower means the balance factor was outside the allowed zone for some ancestor.
Okay.
So
but
you can see
after
that
making the LL rotation, the balance factor at the root B is 0.
Yeah.
So
it's evenly balanced.
yeah. Now the question comes, continue going up. So if I'm making the B as root now, what else do I need to do?
So you look at the parent. So obviously we completely ignored all the nodes that are further up, right from here. We replaced A by B, but then imagine this entire subtree rooted at B is here, right? Whatever I showed in the last slide is here. This is B. Now maybe
I don't know which one you are pointing to. I can see the case.
Probably.
oh, sorry. So what I said is this B could have any number of ancestors above, right? These haven't changed. It's as if we have frozen the rest of the tree and we are only manipulating this subtree inside it. Having manipulated the subtree inside it, we notice that the overall height of this subtree has reduced. So this red subtree, which was initially skewed, has now been balanced well, but it's become a little shallower. So now the parent of B, let me call it PB, maybe the parent of B had another subtree here, the right child had another subtree here, and the balance factor here could have been -1 already. Right? That means when the height of this tree was h plus 3, the height here was actually h plus 2, sorry, h plus 4. If it was h plus 4, that means PB, parent of B, already had a balance factor of -1. And when this tree became shallower and it became the height changed from h plus 3 to h plus 2,
Just to
suddenly
-2.
the balance factor here becomes -2.
Okay.
So the same kind of adjustment has to be made. On P of, on the parent of B. So the height there is actually h plus 5 to start with. So what we would call as h would be something different.
Okay.
Right, when we do the analysis for the parent of B.
I have a question though. Do you think in interview, an interviewer is going to ask in detail about any AVL tree? I'm just after going through so much of complexity, I'm trying to. It's a fundamental question.
So yeah, I mean, I don't see the point of remembering any of this, but at a high level, you would have probably taken away the fact that when things are imbalanced, we can do a case analysis and fix things by single and double rotations. So I think that's the main thing. Maybe you can also keep in mind that with insertions, a single, I mean, a one-time rotation, whether it's single or double, fixes things. In the case of deletes, you could still have spillover effects all the way up in the tree. So you might have to, in the worst case, do log n rotations. Assuming that the tree was balanced and you deleted something along the longest path, you could have an effect going all the way up. So up to log n rotations would happen before everything is satisfying the AVL tree structure with the balance factors and all.
Okay.
So, and this should also give you some sense of why you wouldn't be expected to code this up in an interview, because there are too many cases to analyze. Even if the final code is not that long, but it's still going to be relatively long for what can be done in an interview compared to, say, what we did last week when we did binary index trees. The code was just 4 or 5 lines, even though a lot of analysis was required. So here also you could maybe write the code in a way that could be written in maybe a couple of 100 lines, but yeah, so I have had students who have been asking since more than a year why we don't cover balancing. So the reason here was, I mean, the purpose of taking this class was just to make sure that we cover at least one of the trees.
Which is the widely used balanced binary search tree? Is it B tree or B red black tree? I know
red black trees are often used for the in-memory tree maps, and B trees will be used for database database indexes, and there can be other kinds of trees also. Like with sorted string tables and all, there could be um, other kinds of balance trees which can also do some kind of range queries. But yeah, B tree is quite general. Uh, I mean, there are broadly three different ways you can try to balance things. One is height balance, as what we did here, where the height of the left subtree and the height of the right subtree, that should not these two should not differ by much. Another way you can try to achieve balance is by mandating that all the leaves will be at the same level, but in the internal nodes you can actually store multiple keys. It's not going to be just a single key that you compare and go down. So it's kind of like preserving that perfect smooth triangle shaped structure, but adding the flexibility to the internal node, that you can have one key, maybe two keys, maybe three keys. So depends on, so depending on what the smallest allowed number is and what the largest allowed number is, you get trees with different names there, B trees being the most general. And so there, the reason the tree is balanced is because by the time you reach the leaf level nodes, either at each node you're splaying out by a degree of maybe at least two, right? At least two. You can't have an internal node with just a degree of one. If you had an internal node with a degree of one, you would probably merge it with another internal node that has a degree of maybe two or three, so that combining the forces, they have a degree of four or five. So depends on how you define this smaller range or the and the bigger range. You can get trees of which are all going to be log n but different constant factors. And a third way would be to focus on how many nodes there are on either side rather than the height on either side, and that's more complicated. Uh, but red-black trees are so it's easier to understand them if you understand 2, 3, 4 trees. And since I had to take this in a single class, I didn't want to like spend one class on 2, 3, 4 trees and then another class on red-black trees. At least in a single class, you understand how balancing happens. But red-black trees and B trees would be the ones to look for if you want to look at balanced trees that are actually used in.
So do AVL trees, are they used anywhere in our day-to-day data structure? I think of red-black tree in-memory data structure, probably, let's say if you are implementing some autocomplete feature where you have a limited set of data, you can use probably red-black tree, if you're autocomplete.
Yeah, so I'm not sure. I'm sure people are implementing AVL trees for individual applications. I'm not sure if they're available as part of standard libraries, which seem to depend on red-black trees. Yeah, somebody else had a comment.
I think Cisco's whole BGP million routes database is AVL tree, but
Okay.
they have implemented them. It's not some library or open
Right.
source thing.
Yeah.
Correct. In Cisco, AVL tree is extensively used. Even in HAL layer, extensively used for even QoS mapping and stuff like that.
Yeah, so with red-black trees, we saw today that AVL trees have a height that is order log n, but specifically that constant factor was around 1.44. With red-black trees, it's actually a little more. It's around 2 log n or something. So that means the absolute height of the tree is allowed to be more than what an AVL tree would be allowed to be. So that added height and added flexibility, you can say, allows for operations like insertions and deletions to be done without that many adjustments, right? If you have a very rigid, the more rigid structure you have, potentially with every operation you'll have to do some adjustment to preserve that rigidity. Whereas the more flexibility you have with every operation, you can accommodate things without having to rebalance every time. And so if you don't have that many insertions, deletions happening. You have lots of search operations happening. Red black trees can allow things to, I guess, go a little faster as far as the updates are concerned than AVL trees. But if you just wanted to optimize for search, then the absolute height of an AVL tree, because there are stricter constraints on it, would mean that searches will tend to happen a little faster with AVL trees as compared to red black trees. Okay, so yeah, this completes deletion. I do have one small thing to add further, but let me just write here. Time complexity for deletion is order log n for the deleting physical deletion, right, up to physical deletion of node X, and then potentially order log n more time for readjustments up the tree, right? Potentially up to order log n rotations. In the case of insertions, the second part was order log n, and that was just because the updating of the balance factors until you reach a point where the ancestor node is the first ancestor node is found where there is an imbalance. That path could be order log n long, and so that's why we had order log n. Here, not only can you go all the way up, but you could also have rotations happening at many places. So delete for that reason is the most complex among the three operations. Search, of course, didn't change at all. Right. Now, having done this, the symmetric cases can also be done in the same way. We don't have to deal with them separately. Those in turn will be split into three cases, which will be perfectly symmetrical to what we've done here.